Thank you very much for your introduction. My name is Yuma Kawamoto, and I'm an industrial PhD student at LeapWave Technologies under the supervision of Alejandro Rivera Alvado from LeapWave and Guillermo Carpintero from UC3M. As in the introduction, it's a bit outside of the the title of my thesis is Ultra Broadband Wireless Communications Systems Development. It's a bit outside of the aerospace engineering field, but I hope you find it a little interesting. So here is the outline of my presentation, and I'll start with the motivation for my thesis. So there has been a growing demand for high-capacity wireless links due to a huge increase in the data traffic in recent years. And according to Shannon's theorem, in order to increase the channel capacity, we need to increase the bandwidth of the transmission line. And if you want wider bandwidth, one of the possible ways is to move towards higher frequencies. Because, for example, the terahertz, in this terahertz range, starting from 100 gigahertz, there is a vast spectrum available, which is untapped and not currently practically used in the current technologies. And high-frequency signals are attractive to satellite communications, especially for inter-satellite links. Currently, the Ka band from 26 to 40 gigahertz is being used. And these high-frequency bands are attractive because they transmit and receive large observation data, which requires high-capacity communications. And the atmospheric attenuation is almost negligible in space. And antennas are going to be more compact because of the shorter wavelengths. And also, the beam alignment is not strict compared to optical communications. And it can also be applied to sensing and imaging, which is beneficial for space technologies. So the technical challenge in using high-frequency signals is signal extraction and delivery. Here you can see the current interconnection technologies. We have coaxial cables and connectors and the rectangular waveguides. So for coaxial cables and connectors, they provide a broad bandwidth from DC to 220 gigahertz. However, if you look at the photograph, the actual coaxial connectors, they are very tiny, fragile, and it needs even technicians to just connect and release the devices. And it also suffers from high loss at higher frequencies due to the skin effect. So it's not ideal to go beyond 220 gigahertz with coaxial cables. On the other hand, rectangular waveguides offer quite low loss at high frequencies, but they are bulky, very expensive, and offer limited bandwidth due to the dimensions of the waveguides as shown here. So there is no suitable practical platform for high-frequency technologies. And then our approach is to use dielectric waveguides, especially using silicon. And these dielectric waveguides are easily fabricated using a single etching process, and it's very low cost. And they are low loss, broadband, and versatile for developing functional devices such as filters and splitters and so on. So they are quite suitable for high-frequency interconnections, and we are developing devices and systems based on silicon platform. Okay, so I'll talk about the progress on the ultra broadband transmitter. So previously, we developed ultra broadband transmitter using a high-speed photodiode. So we integrate this photodiode chip into a silicon platform, and we package it and we characterize it, and we observe the terahertz, the signals from 50 to 500 gigahertz from a single interface. And we employed it in the on-off keying communication systems. And however, we faced a problem, and the problem was that we observed a ringing in the eye diagram, even at the data rate of 1 gigabit per second. And this ringing is caused by the low frequency resonance in the device, inside the device, which basically destroys the communication. So what we found here is the low frequency resonance is actually caused by two reflection points. One is the diode itself, which is unmatched for broadband operations, and the other is the open-ended transmission line. And we observed in the simulation the similar resonances to the experimental results. So what we propose here is to properly terminate the open-ended transmission line by using a high-frequency resistor and the RF absorber. So, and then in simulation results, you can see that without terminations, almost all the power just goes back to the photodiode, whereas with a proper termination, the reflection is reduced by the 10 dB, and it could eliminate the resonance. So currently, I'm working on the implementation of these elements, and I will work on the communication experiments again. So next, I'll talk about the ultra-broadband detector. We employ a terahertz resonant tunneling diode as a detector. I will skip the detailed explanation of operation principle, but it shows a very unique IV characteristics. There is a negative differential resistance region in this IV characteristics, which means instead of consuming the power like a resistor, it can amplify the signal. So if you combine it with a simple resonant circuit, it works as an oscillator. And if you apply a proper bias point before the negative differential resistance region, the received signal will be amplified, and it works as a high responsivity receiver. So we integrate the resonant tunneling diode chip into a silicon platform, and the simulation results show that although there is undesired higher order modes appeared in the higher frequencies, it shows the high coupling efficiency from 60 to 330 gigahertz for the fundamental mode. This undesired high order mode comes from the thick substrate of the diode chip. So in order to avoid this, it's necessary to use a thinner substrate or structuring the substrate itself. So we package the resonant tunneling diode chip in the same way as we did for a transmitter. And we characterize the device using the developed ultra-broadband transmitter like this. And the measurement results shows that there is a gain-like behavior owing to the negative differential resistance region at a certain bias point, and it shows high responsivity across the entire frequency band. So additionally, we also worked on extending the operation frequency range down to DC by integrating the metal rods like this. So although this is trial experiments and we still have to investigate dispersion or reflections in this structure, but we observed the lower frequency signals compared to without DC extension. So it shows the feasibility of the ultra broadband transmission line working from 0 to 500 gigahertz. So I'll conclude my talk with the future work. So the baseband resonance for the transmitter originates from the tapered slot antenna, which is an open-ended transmission line, and it can be suppressed by the proper termination. And the proper termination may be achieved using a high-frequency resistor and an RF absorber. And the resonant tunneling diode detector was successfully developed and exhibits high responsivity from 50 to 330 gigahertz. The thick substrate can excite the high order modes at high frequencies, so we have to tackle this problem. And also the feasibility of the DC extension was demonstrated by the integrated metal rods. For the future work, currently I'm working on the debug of the transmitters and the other terahertz receivers, such as photoconductive antenna. And for other components, we already designed directional couplers and the modulators and so on. And I'm planning to work on the amplifiers at the research stage, which is a key component in the wireless transmission systems. And finally, I will demonstrate the communications using the developed devices. These are the achievements. So I attended an optical design course and published a couple of conference papers. And I made a contribution to the IP strategy. Thank you very much.
Thank you.